Hello again, Math 200 statistics students. We are looking at 2.4. So if 2.3 was about measures of central tendency, the measures of the center of the data, 2.4 is measuring variation, or the spread of the data, how spread out it is. All right, so the first measurement for that would be the range. We've already talked about that. It's the highest data entry minus the lowest data entry. That is the range of the data. All right, so that is very, very simple. So the range of this, in this example of the starting salaries from Corporation A would be, let's got to find the highest one. That'd be 47. And you got to find the lowest one, which looks like 37. So subtract them, and you get 10 for the range. All right, for Corporation B, let's see, 58 looks like the highest. 23 looks like the lowest. So the range for Corporation 2 is 58 minus 23, which is, I believe, 55. All right, so Corporation B has the highest salary, but it's also has got the lowest salary. So there's a lot more variability in the salaries for Corporation B than there are Corporation A. All right, the next couple of measurements will be variance and standard deviation. These two things are very related. All right, the deviation of an entry X in a population data set is the difference between the entry and the mean mu of the data set. All right, let me explain that. You take whatever data point you want, all right, subtract that with the mean, and whatever that difference is, that is the deviation for that particular data point. So for example, over here, all right, the mean for Corporation A is $41,500. So if you have the data point 41, then the deviation is negative 0.5, negative 0.5. That's in thousands though. So basically negative $500, because that's the difference between 41,000 and 41,500. All right. So you take all those deviations, all right, and what you do is, let me just read this. Consider the starting salaries for Corporation A. The mean is 41.5. The table on the left is the deviation for each salary from the mean. Notice that the sum of these deviations is 0 because some of them are higher, some of them are lower, and when you add them all up, some of them are negative and positive, they're going to come out to be 0. So the sum is 0. So it does not make any sense to find the average of the deviations. To overcome this problem, what you do is you take the square of each deviation, the sum of the squares of the deviations, all right, known as the sum of squares, denoted by that symbol right there, SS sub x. You do that in a population data set. The average of the squares of the deviations is the population variance. All right, let me see if I can explain that. All right, what this means is, let me get where I can draw on this thing. All right, here is the formula. Here's the formula for variance right here. All right, so let's see if we can tell you what this formula means. This letter X right here is any data point in the set. This symbol mu is the mean of the entire set. So you take the difference between that particular data point and the mean of the whole data set. So let's say the mean weight of the class was 180. Let's say that's the mean. That's the mean, mu. All right, let's say a particular student, student 1, his weight was 170. Okay, so what we do is we say 170 minus 180, and we square it. Okay, then we take the next student. Let's say that they weighed 205, and so you say 205 minus 180, and you square it, and you do that for all the students. Okay, dot, dot, dot. So you do that for all the other students. And what this symbol right here means, it means the sum. So that's why we got these addition symbols. The addition symbol, that comes from the sum. So you're summing all of these differences squared, and you're adding them all up. Then you divide by n, the big N. The big N is the total number of data points you have. So let's say you had 20 students in the class, then you would divide that by 20. That would give you what is known as the population variance. Population variance. Now let's go from there to standard deviation. The population standard deviation, notice that the symbol for variance is this symbol here. That is the lowercase Greek letter sigma. This right here is a capital sigma. This right here is a lowercase sigma, and it is squared. So the population variance, the symbol for that is this sigma with an exponent of 2 on it, sigma squared. The population standard deviation is also the lowercase Greek letter sigma, but it's not squared, it's just a sigma. That's how these two things are related. The population standard deviation is the square root of the variance. The variance is the square of the standard deviation. Okay, did you hear that? The standard deviation is the square root of the variance, or you could say the variance is the square of the standard deviation. So if you calculate the variance, then the standard deviation is simply the square root of that. So it's the same exact formula with a square root over the whole thing. The standard deviation is usually the preferred measure for the variability of a data set, because it's a little better than the variance because it has the same units as the data set itself. So like if you just did the variance up here, the units for that would be dollars squared. Okay, which is kind of strange to even think about. But when you take the square root of the variance, the standard deviation, the units for that is back to dollars again, which makes more sense. So the standard deviation is usually the preferred statistic. It's usually the preferred measurement to measure the variability of a data set. Some observations are, again, we said the standard deviation measures the variation of the data set about the mean and has the same units of measure as the data set. So it's giving you basically like, it's kind of like an average distance of each point from the mean or from the middle of the data. It's kind of like giving you that, a standard deviation of the data set. Standard deviation is always greater than or equal to 0. When sigma equals 0, the data set has no variation and all entries have the same value. So if everybody weighed the same thing, if everybody weighed 180, then there's going to be no variation at all, and you would get a standard deviation of 0. All right. But as the entries get farther from the mean, if they get more spread out, the value of sigma will increase the more spread out the data are. Okay, now to find the variance and standard deviation can be a pretty darn tedious thing to do by hand. So this is like all the steps that you have to do to find it. Pretty lengthy process to find the standard deviation or variance by hand. But the good news that I have for you is that your TI-84 calculator can find it quickly and easily for you. So I think I already told you about that the last time we had a video. You do the one variable stats after you've put the data into L1, and you do the one variable stats. It gives you the mean and the median, and it also gives you the standard deviation. All right, so example 2, finding the population variance and standard deviation. Find the population variance and standard deviation of the starting salaries for Corporation A given in example 1. All right, what you would do is put all of these into L1. Let me just do that. I'm going to pause it and put them in there. In case you've forgotten, what you do is you hit Stat, and then you want to edit a list. So you click on Edit, hit Enter. And then here's L1. You just put all these things in there. 41, Enter. All right, I've entered them all. I'm going to hit Stat again. I'm going to click to the right to the Calculate menu. lots of things I can calculate. I'm going to calculate the one variable stats for that data set. The list is L1. The frequency list, there's not one. We don't have a frequency list there, so leave that blank and hit calculate. And here are lots of good stats. X bar is the mean of that data set. All right, this is the sum of all the data, 415. The sum of the squares of all the data, 17,311. You usually don't ever use those. All right, the capital S sub X, that is the standard deviation of the data set if it is a sample of data. Whereas this Greek letter sigma sub X is the standard deviation of the data set if it is the entire population that you have entered. So for the data that we just entered, that was all of the salaries for Corporation A. It was not a sample. It was every starting salary that they had. Therefore, it was a population. It was not a sample. So we would look at sigma sub X. So our standard deviation is 2.97. Okay. If Corporation A had a ton more starting salaries, if it had like 1,000 of them and we only entered this amount, then it would be a sample that we had entered. And so our standard deviation would be 3.14 instead of 2.97. So you have to be aware of that. What am I putting in here? Am I putting in, is the data I'm putting in, is it every single thing from the thing that I'm studying, or is it just a sample of all the things that I'm studying? All right. And that's how you tell which one of these you should even be looking at, because the formulas are a little different for a sample standard deviation than it is for a population standard deviation. All right, n equals 10, that's the number of data points that I have in there. The minimum of the data is 37. We'll talk more about Q1, Q3. There's the median, and the max is 47. All right, back to the book. All right, notice that the sigma that they found, that is the standard deviation, and they put that it is about 3.0, and we said 3.14, which they rounded it to 3 instead of keeping it at 3.14. All right, if you wanted to get the variance from there, what you would have to do is square that. So if the problem asks you to find the variance, what I would do is I would find the standard deviation in my calculator and then square that answer. So I would have to raise this to the second power to get the variance, which is about 8.9. All right, so the standard deviation is about 3, which in this case represents thousands of dollars. So about $3,000 is the standard deviation for starting salaries for Corporation A. Let me read this little part to you. All right, the formula shown on the next page for the sample variance S squared and the sample standard deviation S. So instead of sigma squared and sigma, it's S squared and S. You use S for a sample standard deviation, and you use sigma for the population standard deviation, just like we use mu for the population mean, and we use X bar for the sample mean. So usually we're using, if you notice, we're using Greek letters for population statistics, and we're using English letters for sample statistics. To find S, the formula uses X bar. Also, it's divided by, not by n, but by n minus 1. Y divided by 1 less than the number of entries. In many cases, a statistic is calculated to estimate the corresponding parameter, such as using X bar to estimate mu. Statistical theory has shown that the best estimates of sigma squared and sigma are obtained when dividing by n minus 1 instead of by n in the formulas. Now, to prove all that is beyond the scope of this course. If you want to know more about that, you're going to have to take a graduate course in statistics to know all that. So I'm sure you won't be too disappointed to find out that we're not going to go into why. But here is the sample variance and sample standard deviation formulas. But again, it tells you that in your calculator. If you're looking for the sample standard deviation, what do you look at on your calculator? You look at the letter S. If you're looking for the population standard deviation, you look at the Greek letter sigma in your calculator. All right. Look at example 3. In a study of high school football players that suffered concussions, researchers placed the players in 2 groups. Players that recovered from their concussions in 14 days or less, placed in group 1. Those that took more than 14 days in group 2. The recovery times for group 1 are listed below. Find the sample variance and standard deviation of the recovery times. All right, we would just do that in our calculator. All right, the question would be, should we take the sigma or should we take the S? Well, does this represent all players, all high school football players that suffered concussions? No, it does not. Therefore, this is not an entire population of data. This is a sample. This is the data of a sample out of a population. So we're not going to look at sigma. We're going to look at S to get our standard deviation. All right, the next example 4 shows you exactly what I've just showed you already. It shows you how to find the standard deviation using the TI-84. So I'm going to skip that since I just already did that in the previous problem. All right, interpreting standard deviation. When interpreting the standard deviation, remember that it is a measure of the typical amount an entry deviates from the mean. The more the entries are spread out, the greater the standard deviation. All right, look at these problems right here. Look at these graphs. Which one of these distributions, the left, the middle, or the right, which one is going to have the highest standard deviation? I think it's going to be the one on the right here. Why? Because most of the data is more spread out from the middle. It's more spread out from the middle. There's more data points, more higher bars out here at the edges. So it's going to have a higher standard deviation because it's so spread out. Which one's going to have the lowest standard deviation? The one on the left here. Because all of the data are grouped right here in the middle. In fact, the standard deviation for that is 0. There is no variability. All the data are the same. And the one in the middle here will have the a standard deviation that's kind of between these other two, because that more of the data is grouped in the middle, but it does have some data grouped on the side as well. All right, example 5. Without calculating, estimate the population standard deviation of each data set. All right, looking at this one, looking at the one on the left, all of the data are in the middle. So what do you think the standard deviation is going to be? It's going to be 0. All right, look at this middle one. Okay, how much does each of these, what is the middle of this data? Let me say that. The middle of the data is right here at 4. Well, how much does 3 vary from 4? It varies 1 from 4, right? How much does 5 vary from 4? It's also 1 away from 4. So what's going to be the standard deviation? It should be about 1, because that's how much the data typically vary from the middle in that data set. All right, let's look at the one on the right here. All right, let's look. The middle of this is also about 4. The 3 is 1 away from 4, and the 1 is 3 away from 4. Well, what's halfway between 1 and 3? 2. So the average over here on the left is about 2 away. Well, look at to the right of the middle. The 5 is 1 away. The 7 is 3 away. So that should average about 6 away. I'm sorry, that should average about 6, which is about 2 away from 4. So on the left side is about 2 away, and on the right side the average is about 2 away. So the standard deviation, I would think, would be around 2. It may not be exactly 2, but it would be around 2. And so that should be what my estimate of the standard deviation would be. I could calculate the standard deviation to get a more exact answer, but that's just to kind of give you a feel for it. All right, let's read this. Data entries that lie more than 2 standard deviations from the mean are considered unusual, while those that lie more than 3 standard deviations from the mean are quote-unquote very unusual. Unusual and very unusual entries have a greater influence on the standard deviation than entries closer to the mean. This happens because the deviations are squared. That's why the standard deviation up here is not exactly 2, it's a little bit more than 2. Because the farther away you get, the more it wants to pull on the data, because it's a squared deviation. All right, so let's go on to the next page. That's enough of that. All right, here is something called a bell-shaped curve. we're going to study this really in depth. Not right now, but really in depth when we get to, I believe, chapter 4, I think. But here we're going to look at it just a little bit. Many real-life data sets have distributions that are approximately symmetric and bell-shaped. For instance, the distributions of men's and women's heights in the United States are approximately symmetric and bell-shaped. Later in the text, you will study bell-shaped distributions in greater detail. However, now, the empirical rule can help you see how valuable the standard deviation can be as a measure of variation. The empirical rule says this: for data sets with distributions that are approximately symmetric and bell-shaped, the standard deviation has these characteristics. About 68% of the data lie within one standard deviation of the mean. So whatever the mean is, and whatever the standard deviation is, 68% will lie within one standard deviation of the mean, either higher or lower. So about 34% to the right and 34% to the left of the mean will be inside of one standard deviation. All right. 95% of the data will lie within two standard deviations. So if you go two standard deviations right here, x bar plus 2s, that's two standard deviations higher than the mean. And here is x bar minus 2s, that's two standard deviations lower than the mean. You add an extra 13.5% in each of those sections, which added to the 68% gives you 95% in total. All right. So it adds an extra 27% to the 68% that we had before. Now, if you go three standard deviations away, that's here x bar plus 3s and x bar minus 3s, you're going to add an extra, 4.7%. So 2.35% here, 2.35% here, and that totals out, if you add it to the other 95%, to 99.7% of the data will lie within three standard deviations of the mean being right here in the middle. All right, here's an example. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States, ages 20 to 29, was 64.2 inches, with a sample standard deviation of 2.9 inches. Estimate the percent of women whose heights are between 58.4 and 64.2. All right, the way I like to draw out a normal curve, draw out this bell curve, and put the numbers on there. So on the middle of the bell curve, I'm going to put the mean. The mean, that's a mu, is 64.2. So I put a 64.2 right there. Then I go one standard deviation, two standard deviation, three standard deviations to the right, and one standard deviation, two standard deviations, three standard deviations to the left. The standard deviation, sigma, it tells me is 2.9. So I'm going to add 2.9, and then add another 2.9, and add another 2.9 as I go to each line. And here I'm going to subtract 2.9 and subtract another 2.9 and another 2.9 as I go to these lines here. All right, I'm going to go ahead and put that on. All right, I just went ahead and added. I added that way and I subtracted that way. I'm just counting by 2.9. I'm counting by the standard deviation. Every time I go to another line, I'm adding or subtracting another 2.9 from that previous line. Now, the empirical rule told me that 68% of the data lie between one standard deviation above and below the mean. So that's going to be 34% here and 34% here every time. All right, another standard deviation covers another 13.5% and 13.5%. And then another standard deviation covers another 2.35% and 2.35%. And those percentages inside of here will not change. The numbers down here will change depending on the information in the problem. My mean depends on the mean of the standard deviation in the problem. Now, okay, I'm trying to find the percent of women between 58.4, which is this line right here, right? 58.4, and what? 64.2, that's this line right here. Okay, there's 64.2. So that's all of this in here. All of this in here is what I'm going to try to find. So all I have to do is add up those percentages. All right, so 13.5 plus 34, that is, let's see, 47.5. All right, 47, is it 40? Yeah, 44 plus 3, yeah, 47.5%. Trying to add that in my head. So let's see here, and it says that here in the book, 47.5% of women would be between 58.4 and 64.2 inches tall. All right. The empirical rule only applies to symmetric bell-shaped distributions, and most of the time the data are bell-shaped. But sometimes it's not. What if the distribution is not bell-shaped? Or what if the shape of the distribution is not known? This next theorem gives an inequality statement that applies to all distributions. It is named after the Russian statistician Pafnuty Chebyshev. Man, you get some great names in statistics. What was some? So maybe these can be really good names for your pets. Call. Hold on just a minute. Let me get my pen going here. So one name you could give your pet would be Ojive. Hey, Ojive, come here, Ojive. Another name you could give is Pafnuty. But another name, maybe the best one so far, is Chebyshev. Chebyshev. And there'll be more to come after that, but what awesome names, right? Okay, so Chebyshev's theorem is the portion of any data set lying within k standard deviations of the mean is at least 1 minus 1 over k squared. And, you know, there's other wonderful math names that you could give to in your household, like Pythagoras, that's a good one, Galileo, Newton, Leibniz. How about Euler, Gauss, and lots of others. So anyway, just think about it. Okay, so you can get the proportion of any data set lying within k standard deviations of the mean by this formula right here. 1 minus k squared. 1 minus 1 over k squared. So, and if k equals 2, I wish my pen would not do that. Why do you do that, pen? It really doesn't make sense to me. Doesn't make sense at all. So if k equals 2, then all you got to do is plug 2 in. And so you can say 1 minus 1 over 2 squared, that's 1 minus 1 over 4. Because when you square the 2, you get 4. 1 minus 1/4, and you get 3/4. Or 3/4 is the same thing as 75%, 0.75 of the data lie within 2 standard deviations of the mean. That's for any data set. At least 75% of the data will lie within 2 standard deviations of the mean. If k is 3, plug 3 in for k. 1 minus 1 over 3 squared, that's 1 minus 1 over 9. That's going to be 8/9, which if you get that as a decimal is 0.8 repeating. So that's 88.9% of the data lie within 3 standard deviations of the mean. That's for at least that much lie within 3 standard deviations of the mean for any data set. All right, for the bell-shaped data set, it was more than that, but we're saying it's at least this for any data set. All right, example 7. Using Chebyshev's theorem. The age distributions for New York and Alaska are shown in the histograms. Apply Chebyshev's theorem to the data for New York using k equals 2. All right. So if you apply Chebyshev's theorem here, the mean for New York is 38.8. The standard deviation is 22.5. So what's it asking? For k equals 2, so 2 standard deviations from the mean. So what you do is you take the standard deviation, you multiply it by 2. You multiply it by 2, you get 45. So you say 38.8 minus 45, and that actually takes you below 0. So you can't go below 0 for the age. So you just stop wherever the limit is. You stop at 0 in this case. And then you add 45 to 38.8. And when you add that, you get about 83.8. So what you can say is that at least 75% of the population of New York is between the ages of 0 and 83.8 years old. All right, standard deviation for grouped data. If I were you to do the grouped data, I would do it in the calculator. I would put this column, this left-hand column of X. You could do it by hand and go through all these steps, okay? But if I were you, I'd use the calculator. I would put this X column into L1. I would put the frequencies into L2. Then I would do the one variable stats, and I would for the list, I would put L1, which was my X list, and for the frequency list, I would put L2, which was these frequencies, and I would calculate the one variable stats, and it would tell me what I want. It would tell me the standard deviation and the mean and all the stuff about the data that I want. Okay, so take advantage of your ability to do that on the calculator. When a frequency distribution has classes, you can estimate the sample mean and the sample standard deviation by using the midpoint of each class. All right, so let's look at this. Spending before traveling. What travelers spend in preparation for personal travel each year? It has put us into this chart right here. Okay, so 380 travelers spent less than 100. 230 travelers in this sample spent between 100 and 199. 210 travelers spent between 200 and 299. So what it's telling us to do is telling us to do the midpoint for each class. So in my X column, I will put the midpoint. The midpoint between 0, it says less than 100, so between 0 and 99, the midpoint would be 49.5. Between 100 and 199 is 149.5. So this X column is all the midpoints of these classes given in this graphic. The frequencies are these numbers. It's 380, the 230, the 210. That's how many people fall into that class. And then again, what I would do, instead of doing all this work by hand, do the one variable stats with L1 and L2. Okay. Coefficient of variation, another thing we need to know. To compare variation in different data sets, you can use standard deviation when the data sets use the same units of measure and have means that are about the same. Okay, standard deviation is good to compare data sets when the units of measurement are the same and when they have the same mean or about the same mean. But what if a data set has different units of measurement or very, very different means? Then to compare the variation of the data, I want to use something called the coefficient of variation. All right. So if you're comparing the variability of data sets for populations, you use this formula, which is and for a sample you use this formula. The formulas are exactly the same except you're using sigma over mu, whereas for the sample you're using S over X bar. Those mean the same thing though, right? It's just sigma is the standard deviation for the population, mu is the mean for the population, S is the standard deviation for the sample, X bar is the mean for the sample. And notice on both of them you multiply it by 100%. All right, so here is a good example. We're going to compare the heights and the weights of a basketball team. The question is, which one of these is more varied, the height or the weight? Okay, so notice they calculate the mean. And probably what they're doing is they're doing the one variable stats for the height to calculate the mean and the standard deviation for that, and the one variable stats for the weights to calculate the mean and the standard deviation for that. Now, since this is all the stuff on the team, it's the entire team, this is a population, not a sample, because it's the whole team. Okay, So the coefficient of variation for the height, you can calculate it to be, the mean would be 3.3, sorry, the standard deviation would be 3.3, the mean would be 72.8, and then divide them and multiply by 100, you get 4.5% to be the coefficient of variation for the height. For the weight, the standard deviation turns out to be 17.7. The mean turns out to be 187.8. You divide them, you multiply by 100%, you get 9.4%. So which one is more varied? I think we could say the weight is more varied because it has a higher coefficient of variation, 9.4 compared to 4.5. And that is it for section 2.4. Good luck on that assignment. I'll see you again in 2.5.